Hello, am I audible? Good evening, everyone. I'm Aditya, and today I'll be your host. I'll be taking you through this session called Algorithms Unpacked. Now, before we start, a quick question to the audience. How many of you have opened a coding problem, read it once, twice, and still had no idea where to begin? That's completely normal. Most people don't struggle with coding, they struggle with how to think. That's exactly what we're going to fix today. So I'll be your speaker. I'm Aditya Srivastava. I'm a first year student at VIT Vellore. I am pursuing a bachelor's in computer sciences and engineering, and I'm really, really intrigued by algorithms. So, an introduction. Today's session is going to be an interactive session, and we'll approach and solve problems efficiently. So, this is not a competition. You're not here to solve as many questions as possible. We'll relax, slow down, how to approach them, how to think, and how to improve them. By the end, our goal is simple. You should feel more confident when you see a new problem. You should be able to think how to approach it. So, what is an algorithm? Simply put, an algorithm is just a step by step process used to solve a problem or to perform a simple task. Think of it like a recipe. You put ingredients in, you perform some steps, and a dish comes out. And in programming, better algorithms don't just solve problems, they solve them faster, cleaner, and smarter. That's the difference between writing code and writing good code. All right, guys, that's enough theory for today. Now, first, let's discuss our problem set for the day. The problems we're going to be tackling today are first, palindrome number that is lead code 9, missing number that is lead code 256, add digits, lead code 258, product of an array except self, that is lead code 238, subarray sum equals k, that is lead code 560, set matrix zeros, lead code 73, trapping rainwater, lead code 42, and median of two sorted arrays, lead code 4. Problems will be gradually increasing in difficulty, so we'll be stopping everything down, relaxing, and stop solving everything step by step. Now, moving on to the first problem of the day. Our first problem is palindrome number. We shall look at the problem statement. The problem statement states, given an integer x, return true if it's a palindrome and false otherwise. Now, before we jump into the code, first we need to understand the problem, what it asks us. First step is to understand what is a palindrome. A palindrome is simply put, a palindrome is something that reads the same forwards and backwards. For example, let's take the number 121. From left to right, it reads 1, 2, 1. And from right to left, it reads 1, 2, 1. So it's true. But on the other hand, if we take negative 121 from the right to left, from left to right, it reads minus 1, 2, 1. But from right to left, it reads 1, 2, 1 minus. Since it's not the same as the original number, thus it will not be considered a palindrome. That's where our thinking starts. We've already tackled the first step, that is understanding the problem. Now, we could the simple brute force way which we're going to be doing today is to just reverse the number and complete the original. And first of all, we're going to think of the edge cases. That is, some cases which will return false immediately. For example, negative numbers which at all cannot be palindrome due to the minus sign. So now moving forward from this, the plan for us would be to basically extract each of the digit of the given number by dividing it by 10 and building a reverse number using multiplication and addition, and then to compare it with the original number, and if it's equal to the original number, we can say it's a palindrome. Doing this would be to ensure that no integer overflow occurs. You may ask me, what is an integer overflow? Integer overflow is a problem that we face if any integer value is greater than the highest permissible value in the language we're using. We should be looking at that too. Uh, So this is the code. Let us first have a little demonstration. Um, So, so this is our lead code page. This is how it happens. This is where we can see the code. We run the code and then go to the test cases. And then wait 1 second. Let me put it back properly. Line palindrome number. Yeah. So this is our code for palindrome number. We run the code and we look at the test cases. It passes all of them. These are the two cases we discussed. This is the third case, that is 10. Now from left to right, it's 1, 0. From right to left, it becomes 0, 1. That is why it is false. Now let us understand the code step by step. The first step is to create a function, a Boolean function, which returns, which takes an integer x and returns a value true or false, whether or not it's a palindrome. Now, uh, after creating our function, we'll be initializing some values. That is n, which would be the copy of the original number, d, that would be the last digit we'll take, and k, where we'll be storing the reverse number. Now k will be initialized to 0, as initially the reverse number will be equal to 0, and when we iterate through the loop multiple times, we'll be adding digits manually so that we can get the reverse number. So first thing first, as we checked for the edge cases, we have to check whether x is negative. If x is negative, it'll return false, since a negative integer cannot be a palindrome number. Then we'll store n in x. So we don't modify x. We can also store the x value to compare later on. Then we move on to our loop. That is while n. That means while the number is still n. And so first we'll take d. D we initialized as the last digit. So d would be n modulo 10. And now the modulo function gives us whatever remainder comes when we divide a number by another number. So in our case, we'll be dividing our integer n by 10, which will give us the last digit of the number. Then we check for our the important check I mentioned of integer overflow. We have to check for that. That is, if k is greater than this value minus d divided by 10, we'll return false. The value which you can see is a hex code for the highest permissible number available in the C language. So if k is bigger than that, it'll return false. After this, we move on and we put k is equals to k times 10 plus t. This will give us the reverse number. In the first iteration, k will be equal to 0 initially. Then we'll add 0 times 10 plus t. That would be, in the case of 121, 1. So k will be equal to 1. And then after which we divide n by 10, removing the last digit, so that the original tens digit becomes the new units digit, and the original hundreds digit becomes the new tens digit. Now, what this will do for us is that in every iteration, we'll be able to save k as the reverse number. Finally, we'll return whatever value we'll get if we uh, compare k and x. Return k is equals to x. This will give us true if k is equals to x, and will give us false if k is not equal to x. These are our test cases, that is 121 and minus 121. So what was our takeaway here? Not the code, it was the thinking. We have to start simple, handle edge cases, ask what can be optimized, reduce unnecessary work, and that is how you approach problems. Now let's move on to a problem where instead of loops, we use pure math to simplify everything. That is problem number two, missing number. So the problem statement states, given an array nums containing n distinct numbers in the range 0 to n. What does that mean? That means we'll be given an array named nums, which will contain distinct numbers from the range 0 to n. For example, if the range is 1, 0 to 5, it can contain 1, 2, 3, 4, 5. And we have to, and then it states, return the only number in the range that is missing from the array. What does this mean? This means that, for example, if we are given an array 0, 1, 3, so our range would be 0 to n equals to 3. So, and in the array, the missing number is 2. We have to return 2. So it seems simple enough. How do we generalize this efficiently? A brute force method would be to check each number, but that would be highly inefficient and it would be quite slow. Now, here's an important observation. We already know what number should be there from 0 to n. And we also know something better. From our high school algebra, we know how to calculate the total sum of all the numbers from 0 to n. So, so a simple method we could do to solve our problem is to calculate the sum using our formula from 0 to n, and then calculate the actual sum of the array. Then, if we subtract the missing number from, then if we subtract the expected sum from the formula, and subtract the actual sum of the array from it, we get the missing number. Think of it like this. If you know the total marks of a class and you know the marks of all the students present, the difference would tell you what's missing. It's the same idea here. This is our code for this problem. Let's move on to the demonstration. Hang on. Yeah, 1 second. That's our problem. Given a number in the range 0 to n, return only the number which is missing. This is our code, and we run for the test cases. This is the initial example that I took, 0, 3, and 1. Let's take a bigger example. So basically, let's take some other example. That is 0 and 1. For this, the formula would be 0, the range would be 0 to 2. And from the formula, we get the value 1 plus 2, that is 3. And the sum of the actual array would be 1. So when we subtract 1 from 3, we get 2, which is the missing number. Similarly, in the first case, the given array is 3, 0, and 1, which is in the range 0 to 3. From the formula, we find the sum of the first three numbers to be 6. And when we calculate the actual sum of the array, we get 3 plus 1, which is 4. We subtract 4 from 6 and we get 2, which is the missing number. So for our takeaway for this question, so first of all, let me explain the code line by line. So first we create a function, missing number, which takes the value of nums and num size. Num size is the size of the array, returns the missing numbers from the range 0 to n. Then in the second line, we take a variable expected and we calculate the sum of all the numbers from 0 to n using the formula n times n plus 1 divided by 2, assuming no number is missing. Then we initialize a formula variable sum is equals to 0 so that we can store the actual sum of the elements present in the array, and we iterate a loop which calculates the sum of the array. That is, we start from the 0th index and go to the final index, and we add all the numbers, giving us the sum of the actual array. Then we return expected subtracted from the sum, which gives us the actual missing number. These are the test cases we discussed. So now, what was our takeaway from this problem? Sometimes the smartest solution is not iterative; it's mathematical. Always, while solving problems, it's advice to ask yourself: Can I avoid loops? Can I use a formula? Can I simplify the problem? Now we're going a step forward. What if a problem looks iterative, but actually has a hidden pattern, has repetition to it? That brings us to our third problem for the day, which is problem three, add digits. Moving on to the question statement. The problem statement says, given an integer num, repeatedly add all its digits until the result has only one digit and return it. What does this mean? For example, let's take a number num is equals to 38. What do we have to do? We have to add the digits of 38 till the time it reaches a single digit number. So first we add 3 plus 8, giving us 11. Now, since 11 is not a single digit number, we got to add the digits again, which is 1 plus 1, giving us 2. So our output would be 2. This is a simple process. Just keep adding digits 1 until one digit remains. Now, first thought while solving this would be to prove first, we extract digits using modulo 10 and then add them, repeat the process. That works, but there's a problem. We're looping again and again, and that's unnecessary. Now, this is where things get interesting. This is where we see the beauty of mathematics. Instead of blindly repeating the process, let us observe a pattern. Let's first try a few numbers. Everybody, I request everybody to try with me. Visualize 10. 0 plus 1 plus 0 gives us 1. 11. 1 plus 1 gives us 2. 12. 1 plus 2 gives us 3. 18. Moving forward to 18. 1 plus 8 gives us 9. And then we go to 19. That is 1 plus 9, which gives 10, which gives 1 plus 0, which gives 1. Do you see it? That's the pattern. The results repeat. This is called the digital root. All numbers reduce to values when added with their digits from 1 to 9 in a specific increasing manner, and the pattern repeats after every 9 digits. So instead of looping, we can directly calculate the result, and that we can do with a very beautiful formula, which is the digital root formula. That is 1 plus number minus 1 modulo 9. And there is one more edge case. If number is 0, we got to return 0, since we cannot divide minus 1 by 9. This is powerful. The way we thought, we converted an iterative problem into a constant time solution. No loops, no repeated work, just one simple line. This is our code. Let's move on to the demonstration. Add digits. And this is our code for add digits. It's a very simple code, very short yet very powerful. We run the test cases and we see what we saw with 38. The expected output is 2, and we get the output 2, and our edge case 0, for which the expected output is 0, and the output we get is also 0. To explain, let me explain this code to you line by line. We'll move step by step. In the first line, first, we have to create a function which will take an integer num and return a single digit result after repeatedly adding its digits. Now we move on to our first edge case, one and only edge case. That is, if the number is 0, we directly return 0 because the digit sum is already 0. We do it by if condition. If the number is equal to 0, we return 0. Then we use our digital root formula, which uh, helps us by reducing the loops and iterations we have to do by one single line, which gives us a constant time result. And we return 1 plus number subtracted by 1 modulo 9, giving us our results. These are again the test cases we could see. So, what is our takeaway from this problem? That is, not every problem needs loops. Sometimes the solution is hidden in patterns. It's just our job to spot it. Now, we're moving on to the mediums. Let's move on to something more practical, array based problems. That brings us to the first problem for the day, product of an array except self. The, prob- uh, the problem statement says given an integer array nums, return an array's answer such that the answer I is equal to the product of the elements of nums except nums I. What does this mean? Basically, this means that if in an array we're given for any index I, we multiply all the other numbers and return that value. So the product, and it is also that is just a single loop. So our thinking process would be, first thought anybody would have would be to take the total product of all the elements and divide by the current element, but it would fail as the array contains, what if the array contains 0? Then we cannot divide by 0, thus resulting in a failure case. So one key observation you have to make is the product of every array every array element except a specific index would be equal to the product of the elements on the left times the product of the elements on the right. So our plan would be to split the problem into two parts. First, we store the product of the elements on the left, and then we store the products of the elements on the right. Hello, is my screen visible to everybody?
Yes, it is.
All right. Yeah. So it'll be optimized. We won't need any extra arrays. We'll just use our result case and one variable. This is our code for the problem. It is kind of long, but we'll move through it step by step. Don't be afraid, guys. Let's first see a demonstration. We go on lead code and we select product of arrays except self. So this is the problem. We get an example of how of an array 1, 2, 3, 4, and the output would be 24, 12, 88, and 6. That means for the first number, the array's multiplication would be 2 into 3 into 4, that is 24. For 2, the array multiplication would be 1 into 3 into 4, that is 12. For the for 3, the array multiplication would be 1 into 2 into 4, that is 8. And for 4, the array multiplication would be 1 into 2 into 3, that is 6. So let's run our code and look at some test cases. This is our first test case, and that is our second test case. So we see in this test case, one of the indexes is 0. Now it's very important. So if any of the index is 0, the product of all other indexes would become 0, as 0 is the multiplicative identity. So we get for -1, it'll be 0, minus for 1, it'll be 0. But for 0, since it's the index times 3, which will not result in 0, but rather in 9. And then moving forward again for -3, it'll be 0. And from +3, it'll again be 0. And from +3, it'll again be 0. Now let us understand this code. Uh, First, we create a function that is product expect self. It takes an array nums and it takes the size nums size. So for iteration, and then a pointer return size where we can store the size of the output array. It will give us the pointer to the result array. So secondly, we have to uh, make sure the return size is equals to the number size. That is the return size array points to the num size value. Then for result, we have to allocate memory ourselves since we're using C. So we use the malloc function to allocate memory for the size of the output array and the result arrays to store the final values. We I For the result of ith for the first index of the result array, we initialize it to 1, which is the multiplicative identity, and then we start a for loop which gives us which we start with 1, and we can't start with 0 since we have already initialized the first zeroth index for the result array. So we start with 1, and then we iterate from 1 to the index less than the number size. So firstly, uh, this is our first pass where we multiply all the elements on the left of the index I. That is, result I would be equal to result I minus 1 times the numbers I minus 1. So this, what we use is called a recursive function, which will iterate again and again, giving us the value of the left array, left elements. And then we go on and we create a variable right, and we initialize to 1. This block will now calculate the product of the elements of the right using right. And for this for loop, I would be equals to the num size minus 1. That it'll start from the end, and I should be greater than or equal to 0. And it'll decrement after each value. Then result will be equal to the value of the we'll store results as result I would be equal to result I times right, and right would be equal to the multiplication of nums. So basically, it'll give us the product of the right array, and these are some of the test case that we have seen already. So what was our takeaway from this problem? This problem teaches us to break the problem into parts, reuse results, and to avoid redundant work. Here, we rather than taking each element individually and multiplying it and dividing it by another element, which would also result in a failure case. If one of the elements was 0, we smartly uh, took the index and we iterated around it. That is, we took the multiplication from the left and to the right, so we could get further two smaller problems, like how we do the merge step, do the break step in merge sort, and then we merge both of them so that we could get a final result. Now let's move on to something slightly more tricky: subarrays. That is the fifth problem. Subarray. Subarray sum equals k. The problem statement says, given an array of integer n nums and an integer k, return the total number of subarrays whose sum is equal to k. A subarray is a contiguous non-empty sequence of elements within an array. So what does this mean? For example, if we've given an array 1, 1, 1, and the k is equals to 2, valid subarray would be 1, 1, and 1, 1. Here we get two subarrays because the order and the index of the array elements would matter. That is, the first one would be the first two ones, and the second array would be the last two ones, giving us the output 2. So how do we approach this problem? A subarray is defined basically by a start index and an end index. A brute force logic to this would be to try all the possibilities, fix a start index, expand till the end, keep adding elements, and for each start, and then keep adding elements, and then do it for each start and each element. But that would take a lot of that would take a lot of time and a lot of computational power. So how would you do it efficiently? Now, rather than recalculating the sum every time, we could keep running a current sum, and then we could add elements as we extend the subarray. We would check the condition every time we add an element, that whether the current sum is equal to k, and then increment the count, and we'll repeat from all the starts, move start forward, and repeat the process so that we can get all the possible subarrays which equal to k. This is our code. It's is basically uh, one function and two for loops so that we could store the current sum, and then we could iterate from the current sum and add the numbers, and then if the current sum gives us a value, we increment the count. Let us see a demonstration real quick. This was the same code we used, and we run for test cases. We get let's look at the second test case. Um, so the subarray, the value we get is the array is 1, 2, and 3, and k is equals to 3. So the output we get is 2. That is 1, 2, and 2 in 1. Let's move on to the explanation of this code. First, we include a stdioh, that is standard input output library, and then the standard library for C. Then we create a function to get the subarray sum, which would take inputs of nums, the size of the array, and an integer value k, that will be our target. And then it will return the count of valid subarrays. First, we have to store the number of first count. We'll initialize a variable count, and we'll use the variable count to find the number of subarrays. Every time we find a subarray which sums, which the sum of which is equals to our target value, will increment the count by 1, which would give us the number of the valid subarrays. So for the first for loop, we'll start from 0 and then iterate till less than 1 less than the number size of the array. This fixes our subarray starting point, and we then make our second variable, which is current sum, and I initialize it with 0, which will be resetting for each new starting index, so that that basically means for every time, every iteration in the start, the current sum will again become equal to 0. We do this so that we could, rather than allocating multiple memories to store every subarray, we rather reuse the same memory we have allocated to one variable, which will reduce our computational and our storage costs. Then for the second for loop, we start from the end, and we start from the start, and then we iterate from less than this num size. Basically, you can imagine this as two pointers, that is one pointing at the start value and one pointing at the end value. Initially both of them are this at the same point. Then we check whether the sum is equal to our target, and we move it forward, and we move it forward, and we move it forward till the end of the array. So this will expand our subarray from start to all the different positions possible, and we'll be doing this for all of the start values. That means we'll start with the zeroth index once, then we'll start with first index once, then we'll start with second index once, and each and every time we'll go to the end, and we'll check the sums, and if they meet our target value, we'll increment the count by one. So then this is our code for it. That is current sums will equal to nums end. Basically, this means the second pointer, that is our n index for our uh, subarray, would be the element at that index would be added to current sum. And then the second condition would be if current sum is equals to k, we increment the count. So basically, this means that the sum of the subarray would be stored in current sum. And if that sum is equals to our target value, we would increment the count by one. And finally, the function will return count. These are some of the test cases we saw. Another good example of this would be uh, 1, 2, 3, and 5. So for that, when we in the first iteration, 1, 2, 3 would be our arrays. The start and end would be at 1. Then we'll add 1 plus 2, 3 plus 3, 6. Both of the times we got two subarrays which do not equal to 5. So we would not be incrementing count. Count will always be 0 at that. Then for our second iteration of the first for loop, the start pointer would be at now and would now be at second first index, that is the oneth index, that is 2, and at that point it'll start the second for loop, in which the first iteration we'll see 2 plus 2 plus 0. That is when 2 is the only case which is not equal to 5, so count will still remain 2. But as soon as the second iteration happens, we go our end pointer goes to 3, which gives us the values 2 and 3 in the subarray. Now, since our target is 5 and 2 plus 3 would equal to 5, we would increment the count by 1, thus giving us the output 1, which would be our expected output. So, what was our takeaway from this problem? Basically, whenever we're dealing with subarrays, we should think of in terms of start and end. It's preferred to take two pointers so that we should iterate through each and every case, and we should build gradually and take results. All right, guys, we'll be taking a short 5-minute break after this problem, and we'll be returning after that to move on to a problem that is tougher but includes matrices. During the break, also, the floor is open for questions for each and every participant if they want any questions or if they have any questions regarding any previous problems. Hello, everybody. So we're back after the break. I hope you guys enjoyed. So this is our sixth problem. That is a problem including matrices. Uh, the problem name is problem set matrix zeros. So what does the problem statement say? The problem statement says, given an integer m cross n and an integer matrix column to zero. So what is that? Basically, we'll be looking at an example. This is our given matrix, that is 111, 101, 111. So according to the given problem statement, that is, if element is zero, we have to set the entire row and column to zeros. So that means since at the 2 comma 2, since at the position 2 comma 2, that is the second row, second column, there is zero. So problem. You start modifying the matrix too early. Giving us basically making us loop multiple times unnecessarily. These new added zeros originally existed without modifying the matrix immediately. One brute force an arrays to track it. So a smart trick to do it would be to use the first row and the first column as markers. Basically, whenever we find a zero at a position I comma j, we mark the I comma 0, that is the first row, and the position 0 comma j equals to 0. So basically, column so that whenever you loop it again also, you'll already see that it's marked and you would avoid another zero if that occurs. But to this too, there is a special case. That's the catch. What if the first row or the first column already has zeros? For example, if we see in this second example, that is the position 1 comma 1 already has a zero, which is the first row and the first column. So both of them already have zeros. How would we solve this? We would keep track of these using separate flags, and these flags would mark zeros on the first row and column. If a cell is zero, we mark its we store the original zeros in the flags. This will be the only extra computational cost we'll require throughout the program. And after applying our markers and our flags, we could use the markers to set the rows and columns to zero, skip the first row and column for them, and then use the save flag to decide if the first row and column should be zero. So this will be our code. It is kind of big. There's no issue in it. Let us go move on to our first demonstration. That is uh, matrix zero. This is our code. It has three for loops to set the matrix and call set flags, and then for loops to set the matrix markers, and then for then further loops and if statements to make those certain uh, rows and columns equal to zero and returning us the matrix. So let's run our code. Now, given the input matrix, the output is 101 and 000 101, the output we expect. And this is our second case in which the initial first columns would be flagged, which would be later not be zeroed so that it doesn't give a repeated case. And that would give us our second output. So we move on to the explanation for the code. Uh, Firstly, we have to create a void function that would take input from of matrix and the matrix size and also the column size. Then we would initialize rows equal to the matrix size, that's the size of the rows, and variable columns equals to the matrix column size. Uh, then we'll put first row, initialize first row and first column variables equals to 0. These two variables now would be our flags uh, to, uh, to check whether the first row or first column originally contain any zeros. Um, then we come on to our first for loop. That is, it starts from 0 and goes on to the rows, number of rows. If the matrix for I comma 0 is equals to 0, first column equals to 1. Uh, this will check if any element in the first column is equals to 1. If yes, it will mark first column equals to 1. So here first column equals to 1 does not mean that the first column element is 1, but rather it means that the first column has been marked or flagged that the first column has a 0 in it as the first element. Moving on to the second loop, which the second for loop would be for rows, for columns. That is, it'll check if any element in the first row is 0, and if there is 0, it'll mark the first row equal to 0. We move on to the next loop. Here we mark, this is the code we use to mark the rows and the columns so that we can find them later on and then zero them. So first we iterate from 1 to the end of the rows. We iterate from 1 rather than 0 because we have to avoid the first column and the first row in each of them. So then our if condition comes in if matrix position ij is equals to 0, then we put the matrix I 0 equals to 0 and the matrix 0 j equals to 0. That is, if any cell is 0, it will mark the entire row and column using first column and first row. And if a column is marked, set all of its element to 0. That we'll do that by another for loop in which we'll iterate through all the columns and all the rows of the matrix and uh, set the elements 0 to all of the rows and columns which contain one element 0. Then this for the second loop first for the columns. And then if first row, then now we have to check, come back to our flags and check if we had to make them 0 or not. Then if first row originally will be marked 0, originally will have a 0, we'll make the entire first row 0, and we'll check whether the first column has a 0 or not. And if it has originally has a 0, we'll again iterate through the entirety of the first column and make each and every element equals to 0. This would give us the expected values. So once again, we come back to our examples. For example, in example, if we see in example 2, the first row is equals to 0 and position 1 comma 4 is also equals to 0. So if we flag this and then we move on and iterate through all the values, when we reach the position of the second 0, we see that and we mark the entire row and column